Well, good morning. Sorry, my throat's not too good. It's 9:37. Well, we got a student here. Good. Let me adjust the lights and things. About to get started. In fact, I did. Yes, sir. Yeah. You multiply this by that, so you multiply this by that. So put that in parentheses. And say right here. Hold forward. You're gonna have four. Yeah, all the way. Let's do it and multiply. Once you pull it, multiply by 8, 10, 2. You get some last thing that he will lay out.
Before you start, I have a small question from.
You have a what?
Small question from the chapter, the quiz 7.
Right.
The first one. Can you show me how to start the first one? The first question.
Okay. This is on which test?
Chapter 7.
Chapter 7. Is that test 2 or test 3?
It's test 2, but there's
Find the area, is that the one?
even it's in test 2.
Okay, yeah. There were 2 test 2s. I didn't change the number on the one. Okay, still not there. Okay, evaluate the integrals.
Yes.
Okay. All right. Oh. Okay. All right. Let me make a couple of announcements first. Okay. I am recording. Yeah. One needed to find where I was. So let's start the slideshow here. All right. Before we get going. Wednesday's the last day of class. I know you've been dreading it all term, but it's going to be here Wednesday. Okay. So that means on Wednesday I'll be returning everything to you. So be sure you have everything in by then. Okay. I'm saying this on Screencast-O-Matic so everybody can hear it, hopefully.
Yeah.
So also Wednesday is when your research paper is due. You've already turned yours in, but I'm saying it for everybody else. Okay. And also, please do the student course evaluations.
Yes.
Okay. All right. Good deal. All right. That said, then the question was, what? The first question, how to set it up? Is that what you're asking?
Yes. The question is, it's in parentheses, right?
Yeah.
So which one do I simplify that?
Okay. Wait. Just a second. Let me get my black pen up. Okay. The first question, sorry, is this one. The integral from 2 to 4 of the log of x minus the square root of x squared minus 1 dx. Okay. Now, the first thing was, what's your approach? What do you think is going to work on that?
It's integration by part.
Exactly. Okay? So then you're going to say, let u equal something and dv equals something else. Okay? And then you're going to do a du and then a dv. And then a v. Okay. Now, what do you think is going to be what?
That's the question.
This is the one time when you have a log function, usually let that be your u. So let u equal the sorry, the natural log of x minus the square root of x squared minus 1. Ew! What did it do? Okay. And dv just dx. The whole thing. Right.
Then when I'm finding the derivative of like
Yeah, you do the derivative of that, which is,
right?
say again?
I have to do the chain rule?
Yes, you do.
Okay. And the dv is going to be
dx. So
dx
v is going to be x.
x.
Yeah.
So when I'm doing the derivative in log,
Right?
so the first thing I have 1 over
Yes, that's where you start.
x.
Then du is equal to 1 over x minus the square root of x squared minus 1.
And then derivative of the inside,
Right?
it's going to be the chain rule is like literally I don't know why
Okay.
it's so hard for me.
Here's what I would suggest writing this as x minus x squared minus 1 to the 1/2 power. And take the derivative of that then.
So we take the power in front.
Okay, yeah, but first, what's the derivative of x?
It's going to be 1.
1. Minus
1
1/2
half. X to the second minus 1.
to the negative 1/2, right? And then you got one more thing to do. Chain rule one more time. Say again. You got the chain rule of what's inside that.
So it's going to be
2x. Right?
Okay.
Got it? And here the 2's go out. Okay. All right. All right. And can you go from there?
Yeah, then I got
Okay, yeah. Right, yeah, but I mean, you got some more stuff to do here. This is going to have a dx at the end. Okay. And your v is equal to x. Okay. From here, this thing goes to that. Okay. Now, you got a little more work to do here. It's a little messy, but let's try it. 1 over x minus the square root of x squared minus 1 times, now, let me take this for a moment and do this. This is 1 minus x over x squared minus 1, the square root of that, right? That thing in parentheses there is that. Right? The 1 minus, yeah, because it's a negative 1/2, right? So to get this into a rational form, that's the same as multiplying this by the square root of x squared minus 1 over the square root of x squared minus 1. Okay? And then that will be, are you through? Thank you. Okay. So this gives you, okay, just a second. Mark this here. Marcus. Okay. All right. Okay. Did I hear you say what happened to the 1? Where's the minus 1?
It's exactly.
This one? It's still there. All right. Okay. All right. Now, all I've done here is to at least come in the denominator, I multiply, I write this as square root of x squared minus 1 over square root of x squared minus 1. That's the minus 1. That's the one you're asking about. That's the ugly one. Let me clean it up some. There we go. That's a little better, I guess. Okay. Now, what that gives you is the square root of x squared minus 1 minus x over the square root of x squared minus 1. Okay? And that's what's multiplied by that. Right? Because you had that already, and you're multiplying it by this. I just taken this down here, and this has a dx at the end. Okay. And if you'll notice, this and that are almost the same. It's just the minus sign. So you can wipe those out and make that a minus 1. A minus. Didn't need another 1 there. Okay. Okay. From there, hopefully you can go. All right.
Okay, then du is going to be maybe minus 1 dx, right?
du is, this is what I've been working on. The du is equal to, that goes off, and it's minus 1 over the square root of x squared minus 1 dx. Because that's all that's left. Because you see, this is the first part of this. This is the second part when you do the chain rule twice. But then you take this and you figure out what that is, this. And then that and that differ only by a minus sign, so pull that out front. So this is what your du is. Okay. All right. And then from there on, I think you can go. Is that all you needed?
So far.
Okay. All right. Now, let me erase. This was the first question on the last test. Marcus, did you get that? That's what she was asking about. That's the first question on the last test. Yeah, the first part of the first question. There were 2 parts. That was the first part. Okay? All right. All right, to erase it then? Okay. You can go back and watch it. It still will be there. All right, before we go any further, let me make these few announcements. I made them, I think, before you came in. Let me make them again since you got here. On Wednesday, and I know this is sad, but you'll get over it. Wednesday's the last day of class, okay? For this class, I mean, Thursday's also, if you have a Thursday class, right? Okay, so that means I'll be returning everything to you. Now, I won't return your research papers. I have to hang on to those because periodically ask for samples of student writing, so I have to hang on to those. But your test, I'll be returning those to you. So get them in to me by today or tomorrow. I can give them back to you on Wednesday. If you give them to me Wednesday, then you have to come back and pick them up whenever you want to. Yeah, so, which also means, and I forgot to say this before, Wednesday I'll be giving you your final exam, the last test, which will cover as far as we covered today. Right now it's looking like it's just going to be the 3 sections on in chapter 8. That's what it looks like. If we get more covered today, then I'll tell you that too. Okay?
So the final test is not...
It's not comprehensive. It's just going to be on chapter 8, what we've covered since the last test.
Is it a take-home? Or...
Yeah, it'll be a take-home. Yeah. I'll give it to you on Wednesday, and then you bring it back to me. Any time, technically, it should be back by Wednesday, 9 to 10:50, but you can bring it to me anytime, Monday, Tuesday, Wednesday, or Thursday. Do not wait until Friday. Friday, I'm out of town, so I cannot receive it on Friday. Got to get me that final exam. Now, this isn't this week, but next week, by Thursday of next week. And then when I'm out of town, I can grade it. If you give it to me late on Thursday, then I'll be grading it while I'm out of town, but that's fine. I can do that. But grades have to be in Monday after that, so I have to have your papers by the end of the day on Thursday. Okay. So, now, okay, that's the first part. The second part is, have you done the student course evaluation yet? No, please do those. Please do those. All right. Now, example 3, on the bottom of page, no, example 4, sorry about that. The bottom of page 452 or wherever it is in your book. They just sort of show you this pretty picture. The one in your book is a nice, I think, pretty colored picture, and it's the same one that's in your book, which looks terrible. I don't know what they did differently. This one must have been after rain. This was when it's in drought. I don't know. But that picture's a lot prettier than the one in your book, right? Same picture. It's Hoover Dam. At the time it was built, I think was the tallest and probably biggest dam in the world. It's been exceeded since then probably many times, but at the time it was built. It's the Colorado River is what's behind it and continues here. This is before you get to the Grand Canyon, okay? And it provides, it's a hydroelectric dam, I think, built by the government, what is that? One of the things, Department of Energy or somebody, but I don't even think they had a Department of Energy back then. They built the dam, it provides the power. It's probably privately owned now. I don't know the dam is, but the power generating probably is. And that supplies most of Southern California. This is in, I don't remember what state this is in. It could be Colorado, is it? It's Colorado River Bridge. Yeah, it's somewhere, it could be Colorado, but it's somewhere there upstream from the Grand Canyon. Okay? And by the way, the lake behind it is Lake Mead, M-E-A-D-E. And that's one of the deepest lakes because that's one of the tallest dams. There was actually the drought they've had in California before this picture was taken, and the area out there in the west. Lake Mead has gone down probably 2/3 of what you see there. There was actually back, I think it was after World War II, a bomber. They were using it as a reconnaissance plane. They were just training with it, and they were flying along the river. It went down in the lake, and it was so deep they couldn't get to it. Now part of it's sticking up. That's how bad the drought has been there. But that's not what we're talking about here. Okay. But the side of a dam is inclined, and it's really hard to tell from these pictures here. But if you can picture what we're talking about, on the front, the water side of the dam, I think this is pretty flat. But on this side of the dam, the dam comes out, it gets wider and wider and wider at the bottom because that's where the greatest pressure is. At the top, the pressure is not very great. You remember the story of the little boy who stuck his finger in the dike, I think it was in the Netherlands or somewhere, to keep the town from flooding? That was true because if it was near the top of the water line, there's not a lot of pressure. You could put your finger in there and stop it. If it was near the bottom, no way that would work. But this was the story in the but if it hadn't put its finger in, it kept washing away until it destroyed it. Yes. This ends at 11:10. Yeah. Well, I'm teaching class right now, so yeah. Right. Okay. So anyway, the side of the dam is inclined at an angle of 45 degrees. Here's the picture that shows this. Okay. Now, actually, the way they colored it shows is the side toward the water that's inclined. I don't know which is really the case. I thought it was the side on the outside, but whichever, this works as well. Side of a dam is inclined at an angle of 45 degrees. The dam has a height of 700 feet. They haven't got this labeled on here, so I'm going to put the height. Well, as soon as I go to write, it's going to shrink. So let me go and do this. Okay. This height here is 700 feet. That's the height of the dam. Let's just call it H. Okay. We may want to change that in a minute, but right now we'll call it H. Height of the dam is 700 feet, and the width, 1,500 feet, as shown in this figure. Oh, when they say width, I thought they were talking about the width down here. No, they're not talking about that width, they're talking about this width. Okay. So they did label that 1,500 feet. I would say that's how long the dam is. Okay, I wouldn't call that width, but it's fine. Yeah. From that side, it looks like the width. Calculate the force F on the dam if the reservoir is filled to the top of the dam. Water has a weight density of 62.4 pounds per cubic feet. Before we were using 1,000 kilograms per cubic meter, but this is in the English system, 64.4 pounds per cubic feet. Foot. Okay. Now, they're showing the water on this side of the dam, so we're going to have to calculate it that way. What they've done is break the vertical axis from 0 to 700 into N intervals. Okay, so basically you're breaking this. Why is my pen? There it comes. Into N intervals. Okay. Now, every one of those cuts across here. See if I can line two of them up. Okay, right there. And that gives you the intervals. So your intervals are your delta y n times delta y is equal to 700. So your delta y is equal to 700 divided by n. Okay? That's your delta y on this picture. Not that we're going to use it, but okay. Now, your surface area is this. If that's a 45 and this is 90, then this is also 45. Okay? I would put degree sign by it. Okay? And from our knowledge, if that's delta y, these are both 45, this is also, amazingly, delta y. And then this would be root 2 times delta y, because of 90, 45, 45, 90 triangle, the hypotenuse is root 2 times the delta y. Okay? Now, so they've illustrated that here. The vertical distance is delta y, but the horizontally, and oh, they did have the 700 over here. I didn't see it there. Y0 at the top is 0, and yn at the bottom is 700. Okay, so the face there is delta y divided by the sine of 45, but we've already determined that's the square root of 2 over 2, right? Well, we haven't determined that, but it is. So this right here, this length here is delta y divided by sine of 45, which is the square root of 2 over 2. So I'm going to put it that way. Okay? I'm going to put the 2 up top and the square root of 2 on the bottom. Because it's divided by that. Okay? Why they did write it that way, I don't know. Now, the vertical height of the dam is 700 feet. We got that. So we divide the vertical axis, and we got that. Delta y is 700 divided by n. Got that. Somewhere there. There it is. This divides the face of the dam into n strips. By trigonometry, each strip has a width equal to, and there they use a different width. That means the vertical width equal to delta y over sine 45, which they have as root 2, and that's the other way to write this, because root 2 will go into root 2 times, so this is root 2 delta y. That's actually the better way to write it. Okay. So the area of each strip is the length of the strip, which is 1,500, okay, times the width of the strip, which is this thing, okay. And as usual, we approximate the force on the J strip, okay. Now, the term we used before, rho g, that rho was mass density. That you had to include the g in it. This is a weight density. You don't need it. You just use your 62.4, okay. So your force on a given strip here, F sub j, on the j strip here, the strip right here, the force on that strip is going to be your pressure times the area. Where the pressure is your weight density, and that's what they're calling W here. I really don't like that too much, because usually you use weight for weight, W for weight, not for weight density, but we'll live with it, times your Y sub j, okay? That's how high you are. J is increasing going down, so Y sub j. That's your pressure, is the force per unit area, okay, times the area, which was your 1,500 root 2 delta y. Okay? Now, if you were to sum all those up, Riemann sum type thing, from 1 to n, j going from 1 to n, that basically leads to your integral, which would be the force, the total force, equal to the 1500 root 2, and then you need your 64 out there too. They're calling it W. I'll call it W2, but that's your 62.4 pounds per cubic feet, okay? And then your integral is going from 0 to 700. That's from the top to the bottom. Not that it really matters any. And that's all you've got is your y dy. Because your y is from here, and everything else are constants. And your delta y is your dy. Delta y is dy. So what that gives you is, when you do the integration for that, that's a pretty simple integration. Y squared over 2, evaluated from 0 to 700. Oops. All right. Well, 700 squared is 49,000 over 2. Okay. So that would be 28,500. Okay. Times 1500 root 2 times 62.4 times 285,000. Okay, that will give you your total on that. So if you got a calculator, punch those in. By the way, it's an enormous amount of force, as you can tell. $1,500 times root 2 times 62.4 times 285,000. What do you got? It's 62.4 pounds per square feet. That I did it in my head. I hope that's 285,000. Second? 3.77. Okay, now maybe I made a mistake here. Let me see. 49. Did you get it? You finished? Okay. Say again? Oh, you're right. 245,000. You're right. Sorry. I knew something looked wrong there. Yeah. I was multiplying by 2, not dividing. Yeah, how stupid. Yeah, they rounded 3.2824 times 10 to the 10th. Yeah. That's an enormous amount of force, by the way. And dams do hold back a lot of water. Okay. All right, 8.2 preliminary exercises. Do you want to do those or not? No? Okay. Homework exercises here would then be any of the odds. Sorry. Well, I guess just any of the odds 1 through 23. I do some of the easier ones and some of the harder ones. Okay. Now, this next section both of you are engineers, right? Okay. I can't remember about Theo, if he's an engineer or not. He was an engineer also. You're more than likely going to hit something like this. They may not use quite the same terminology, but, and I don't even know they still do this, but back when I was in school, the engineers, instead of an advanced, they took sophomore level physics, but then in the engineering school, they took what was called statics and dynamics. And they used the center of mass a lot, whether they use the same terminology. I think they use similar. I don't know if y'all have to do statics and dynamics or not, but this is where the type of thing you're going to have to be dealing with on that. So let me go on, and doing all that talking, I could have been going to this earlier. This is 8.3. Wish I had done this while I was doing the talking about statics and dynamics. I'm having to sit and wait. It seems like today it's been pretty slow. There we go. All right. This is something you'll never see me do, okay? Pretty incredible. I don't know if you've heard of Cirque du Soleil, something like Circus of the Sun, I think that means in French, I believe. Number one, I couldn't stand if you just had the chair sitting on the floor here. I couldn't do that, but much less on all these chairs. But what he has to do, and it looks really complicated, and it is complicated enough, but the thing is, all you have to do is make sure that the center of gravity is right there, okay? And that's what they've done with this. And that's why he, as if I could do this, is holding himself up one arm. So notice where he's putting his other arm and spreading his legs. He's keeping his center of gravity right over that point of contact, okay? And believe it or not, you can do that. I can't do this. You can do that, okay. But that's because I don't have that strength in that arm to do that. But that's indeed what he's doing. That's what we're talking about, center of mass. There, in the new book, they have, and you probably did this on the playground when you were little, if they had a seesaw or teeter-totter, you know what those things are? Okay. It's a board, and one kid gets on one end, one on the other, and you go up and down. What did y'all call that?
We say seesaw.
Seesaw, okay, yeah. I think up north they call them teeter-totters or something. I've heard it before. It's always been a seesaw to me. Okay. Now, I was always the heavy kid in the class, so I couldn't get on it and do. The other kids would go up, and I'd just be down at the bottom. So what did we do? We moved the board up, so I was on a shorter board and they were on the longer one. And in the new book, they show a ballerina who is usually very, very light and a football player. In fact, it looks like a lineman, okay? It looks like for the Green Bay Packers. So those are big guys, but you could still balance that if you made his board short enough and hers long enough, they could still be balanced, okay? What you're dealing with there is, the linebacker for the Green Bay Packers. As long as you put the fulcrum at the center of mass, they would be balanced, okay? As Archimedes realized over 2,000 years ago, there would be a potential paper topic. I know y'all are both turned in your papers, right? Yeah. So, Theo, okay. Archimedes would be a good one. That's the mass of each object times its distance to the balance point must be equal. So the formula for that, and they don't have the slide here, but okay. There's the board. Here's the football player, big, heavy football player. Here's the ballerina here, okay? You get this concept, okay? She has a mass. He has a mass, okay? This distance is a distance d1, and this distance is distance d2, okay? As Archimedes said, okay, and by the way, they called this, they call it D1 and D2, but they put other things in here too. They call this X1 and X2, the locations of them. And this is the center of mass, which they call X bar. Okay? Now, D1 is obviously, D1 is X bar minus X1, and D2 is X2 minus X bar. Okay? So, Archimedes said that M1 D1 is equal to M2 D2. And when you get to statics and dynamics, they'll call that the writing arm or something like that. They'll have different terms for it. So that's what we're talking about, okay? Now, plugging in what D1 and D2 are, that'd be M1 times X bar minus X1 is equal to M2 times X2 minus X bar. Okay, because you keep everything positive. Okay. Now, if you want to solve for X bar, you have to multiply through M1 X bar minus M1 X1 is equal to M2 X2 minus M2 X bar. If you're wanting to solve for X bar, get your X bars on the same side. So what I would do is add M2 X bar to both sides. Okay. And then add M1 X1 to both sides. Because we want everything, all the things with bars on one side and without X bar on the other. So these go away and those go away. So that gives me M1 plus M2 times X bar, that's these terms, is equal to, okay. And on this side we have M1 X1 plus M2 X2. No. Yeah. M2 X2, yeah. Okay. And then divide both sides by M1 plus M2. And that gives you what X bar is. Okay? Now, M1 X1 plus M2 X2. I left off the 2 here, didn't I? Okay. Yeah. Divided by M1 plus M2. Okay. In other words, the balance point, or the center of mass, they call that COM. That's what it's called here. COM. Now that's a different picture. We'll come to that in just a minute. That's what the X bar is. Okay. I think, let me take that back. They call them the writing moments. Writing, R-I-G-H-T-I-N-G, writing moments. That's what statics and dynamics call it. Thank you. All right. And so they'll refer to moments a lot You'll see that term. You'll get, yeah, there it is in the book too. These quantities, M1x1 and M2x2, are called moments. Okay, so the sum of the moments divided by the sum of the masses, that's equal to the center of mass. Okay, and one way to think of this, of course, center of mass is a length measurement, and this is the moment 1 plus moment 2 divided by the sum of the masses. Well, a moment is mass times the distance plus mass times the distance. So the numerator is mass times the distance divided by mass. That gives you a distance, and that is your center of mass. So it has mass in its word, but it's not the other. Okay. Now, more generally, the moment of a single particle of mass m with respect to a line L is the product of the particle's mass m and the directed distance, positive or negative, to the line. So let me clear this out. I think we beat it to death. And let me write that one. So the moment here's an abbreviation, WRT, with respect to the line L. Okay? Is equal to the mass of the object, that's m, times the distance to L. Now, what distance are we talking about? Always perpendicular distance. Okay? If I were to say, what's the distance between me and Marcus? Okay? I could follow a curved path and go around like that, or I could go around like this. The distance is the line, the perpendicular line, straightest line to you. Okay? That's what we mean, the distance to L, directed distance to L. Okay. The particular, I'm sorry, my throat is, made it through one class okay, but it's not doing too well toward the second class. I don't know what I'll do through the third class today. The particular moments with respect to the x and y axis are noted as the moment with respect to x-axis, the moment with respect to y-axis. Okay. Now, don't get this confused. Those are moments. Just because little m is a mass, big M is not a mass, it's a moment. A mass times a distance. Okay? Kilogram meter or something like that. But it's a moment, not a, don't get it confused with a mass. Okay? So, if you have a point right there, it's with a mass m, then its moment with respect to the x-axis is the mass times the distance to the x-axis. But guess what? The distance to the x-axis from this point here is your y value. Okay? So this makes it a little, to me anyway, a little confusing. And this would be the mass, moment with respect to y-axis is the perpendicular distance from the y-axis, and that is your x value. So, this is a capital M, that's your little m. Moment with respect to the x-axis is my, and the mass times the distance, y distance. Moment with respect to the y-axis is your mx. Okay? So, what if you had several points? Okay, and that's what the second figure 3 here, is actually in our book is figure 4. They didn't have the football player and the ballerina. Okay, what if you're trying to find the center of mass of these 4 points? And you want that center of mass with respect, well, we'll put each of them. Here's your M1, that's X1. Here's your M2, here's your X2. M3, X3, M4, X4. Now, they put the y-axis here and the x-axis here. With those in place, that means your x1 is a negative, right? It's to the left of the origin. So this would be a negative quantity, that would be a negative quantity, this would be a positive quantity, that would be a positive quantity. But you add up all the moments and divide by all the masses. Now this is with respect to the y-axis. You would need to do the same thing with respect to the x-axis. The moment with respect to the x-axis would be, that would be your y1, this would be your y2, this is your y3, and this is your y4. Okay? And your moment with respect to the y-axis would be the sum of all those divided by the total masses again. Okay? Now, we don't know what the masses are. Obviously, I'm thinking they're about the same. Okay? These two distances are fairly small. This one and that one look almost to be the same. This one is much less than this one. So that pulls your center of mass with respect to the y-axis over onto this side. Now, obviously, all your x's are positives here, so it's basically, if these masses were the same, this would be almost the average of those with respect to y-axis. And sure enough, you got two that are greater and two that are less, so that looks like a reasonable expectation for where your center of mass is. Now, I don't know if you're expecting the center of mass to be where either mass was. In reality, they're not. The football player and the ballerina. The center of mass was not where the football player is, not where the ballerina is. It's in here in the middle. So, and quite often with objects and structures and things like this, the center of mass may be some point in space. There's no mass is there at all. But that's the center of that mass. Of those masses would be at that place. See, none of those masses are at the center of the mass, but they define what the center of mass is. Okay. And here is basically what I was just saying. I didn't actually come out this far and say it, but the x component of the center of mass would be your moment with respect to the y-axis, because that's measuring the x distances, okay? The moment with respect to y divided by the total mass, and the y component of the center of mass would be your moment with respect to the x-axis, how far from the x-axis that your y value divided by the total mass. So, these are the kind of formulas you'll be using. Frankly, in my mind, this notation is almost confusing, so I think of it as not moment with respect, but the mass times the x distances. That gives you your m's of y, and this is your mass times your y distances. Okay? I just don't like to think in terms of moments. I'm not an engineer, okay? But in engineering, I think they almost force you to. Okay, but then the total mass is just add all the masses together. Now that example was from a discrete masses. What if you had continuous masses? And that's what, no, I'm sorry, we're going to do discrete first. So here is the first example, I think. Find the center of mass of 3 particles in figure 5. It's our figure 5 in our book, figure 4 in your book, and on the slide set. Having masses 2, 4, and 8 at location 0, 2, that's where your 2 is, 3,1, that's where your 4 mass is, and 6,4, that's where your mass of 8 is. Okay. Now, obviously, these are not equal masses. So you can't say it's going to be sort of a geometric center. It's not. The 8 is going to pull things this way. It pulls it to the right and it pulls it up. So the center of mass is closer to 8 than it is either 4 or 2. Actually, further from 2 than it is from any of the others, too. But that doesn't give you a value. Let's see if we can figure out what it is. Okay? Probably should have blown this up for that discussion I just did. But now let's do the figuring. Okay? Which you want to go for first? X sub Cm. It's the X component of the center of mass. What would that be? Okay. M1 X1 plus M2 X2 plus M3 X3 divided by M1 plus M2 plus M3. See, this is what I'm saying. To me, this formulation makes so much more sense than saying M sub Y. That is M sub Y, but M sub Y says nothing to me. That says it all in my mind. Okay? That makes sense. It's an X. The masses cancel out and you get an X. Okay? Well, what's your X1? This is 0.1, this is 0.2, and this is 0.3. M1 is 2. What's your X1? 0. Exactly. Plus 4. What's your X2? 3. Right? Plus M3 is 8. And what's your X3? 6. All divided by, can I go and add them up? 14? Okay. So this is going to be 12 plus 48, 60. Is that right? I'm sorry? Okay. 12 plus 48 is 60 divided by 14. And if you got a calculator, see what that is. It's something less than... Second? 30 over 7. So that would be 4 point something another, right? Say again? Let's round it to 4.29. I don't know, something like that. And sure enough, it's past 4. Looks like it's past 4, but not as far as 4.5. So let's do the Y center of mass. Y coordinate of the center of mass. And that would be M1 Y1 plus M2 Y2 plus M3 Y3. To me, that's the way, that makes sense over total mass, 14. That hasn't changed. So why reinvent the wheel? Use it. That's still 14. What's the numerator here? Two times 2 plus 4 times 1 plus times 4. Okay, over 14. That would be 4 plus 4 is 8 plus 32 is 40 over 14. That would be 8 over 7. No, goodness, what? 20 over 7. Which would be almost 3, 2 point something. Wait a minute, I did it wrong. 32. Well, this looks like it's great. No, yeah, you're right. 2 point what? 86. Okay. Almost 3. I was looking at that and thinking it was past 3, but it's just short of 3. Sure enough. Okay. So the first one was, what did we say that was? 4.29. Just past 4 and almost 3. That looks right. Now, if you think in terms of moments, you put your x center of mass is m sub y over m, and y center of mass is m sub x over m. Yeah. If you think in terms of that, do it. I think in terms of component, of what that is rather than the symbols. Okay. So they got, 37ths over 27ths. That's what we got to, but we did actual numbers. All right, now we're going to go to another concept here, and this makes everything so much easier. Lamina are thin plates. What do we mean by thin plates? What we mean by that, uniform density. Okay? If we didn't have uniform density, if we had something varying in density as it gets further from some point, then you have a function, a density function to deal with. With thin plates, we just assume everything has a uniform density. And what happens from it, whatever that density is, and the symbol for density, now they're using delta. Before they were using rho. This is any kind of density you've got. Linear density, area density, volume density, whatever density it is, it's going to be delta. Okay. So a lamina is a thin plate of constant mass density, delta. That's a little symbol delta. Capital delta is like the triangle, but little symbol delta is that one. Occupying the region under the graph F at over an interval a to b, where F is continuous and f of x is always greater than or equal to 0. Okay, in other words, you've got something that's always positive z, basically. In our calculation, we'll use the principle of additivity of moments mentioned above for point masses. So basically, we're adding them together, but if you've got a continuum, that turns into an integral. So rather than a summation, it's an integral, just like it's been with Riemann sums. Okay. If a region is decomposed into smaller, non-overlapping regions, sometimes they call these partitions, little delta x's, little delta y's, okay? Then the moment of a region is the sum of the moments of the smaller regions. To compute the moment with respect to the x-axis, m sub y, and again, I find this fairly obnoxious to do it this way, but they do. We begin as usual by dividing a to b into n subintervals, with the width delta x being b minus a divided by n, okay? Just about like always. You're dividing this into n subintervals here, and the delta x is equal to b minus a divided by n. That's what each one of those little increments is. The endpoints at x sub 0 is equal to a, and x sub n is equal to b. Okay? Now, any other point in between there, x sub j is equal to a plus j delta x. Because every one of the increments is delta x, and if you sum j over here, you start at the a point, and then add however many it takes, J times the thickness delta X to get you there. Okay? I can hardly breathe. Okay. This divides the lamina into n vertical strips, and that's what we're seeing here. Okay, this is from your text. I'm sorry. They've left off a figure. Let me see if I can get that. Yeah. This is figure 6, 5 in your book. And what you do, you split the A to B into n equal pieces. And that gives you, the jth piece would be A plus J delta X. That gets you here. And then the height of this is your Y value there. F of that X of J times X of J, that's your, get into that. The shaded strip is nearly rectangular. And how you make it more rectangular is to make smaller and smaller strips, okay? Larger and larger end, smaller and smaller strip. This gets closer and closer to being a rectangle, okay? So the shaded strip is nearly rectangular in area, with the height being F sub X of J and the width being delta X, which we already had figured out what that was, delta X, okay? So that's the area. Now, I'm having trouble breathing. So if you're doing a Riemann sum, okay, now here again, we're doing the moment with respect to the y-axis, which is each of these areas times the distance from that, right? Well, the density is involved with it. And by the way, here it would be an area density is what we're dealing with. I don't think they specify that, but that's what it would be. Because if you can think of it this way, that's an area density. Oh, yuck. I've got to get out of this. Okay. The density is the mass per unit area. Okay. It looks like a pressure, but it's a mass density. Okay. Multiply that by the area, and you get the mass, right? Okay. So the area here is that height, y is equal to F of X sub J, whatever X sub J that is, times your area, which is your width is delta X. That would then be your area. Multiply that by your density, okay? So density times the area, F of X sub I, delta X, okay? This gives you your mass of that strip. I'm sorry, it's getting worse. Okay. Clogging up too. I think it's getting colder in here. But anyway, this morning the students were taking their jackets off. Now what I'm afraid happens is overnight they turn the blowers off, and so actually the rooms kind of warm up a little bit, and then they blow them on, and then it cools off. I don't know. It's kind of nuts. Or else it's always the same temperature with the air blowing. It makes it feel cooler. You lose it's your wind chill. Okay. This would be your total mass. Okay. This would be your mass. Now, Your moment would be that mass times this distance. So multiply this by the distance x sub j, and this gives you your moment. That would be your m x sub j, okay? The mass times that. And that's how I like to think of it. They call that the m sub y, which is your moment with respect to the y-axis, which is exactly the same thing. So, what is the formula then? That moment with respect to this is what they're calling m sub y, okay? Moment with respect to the y-axis. So I guess I'm going to have to bite the bullet and call it that, okay? And that would be delta is a constant because this is a laminar plate, and it's the integral of x f sub x dx. So that's basically what it gets down to. This basically is your mass, or the mass component, mass per unit area. This is the area, this is distance from the y-axis. So this is going to contribute to, that's your m sub y, which, yeah, so just think of it that way. Now, divide this by, what was your total mass? Your total mass was everything except that. You didn't have the x sub I in it. You sum that, and that would be integral of f of x dx, okay? Your length times your width, okay? Times your area density. Notice here your lambdas go out. I mean deltas go out. It doesn't matter what that density is. It's going to be the same in the numerator as in the denominator. As long as it's uniform density, they go out. Later they'll say, let's just assume it's 1, which is as good an assumption as anything. But that's why you don't have to mess with that anymore. And this then gives you your x component of your center of mass. Because look at it. It almost looks like this would divide out this, divide out that, and that gives you your average x, okay? And indeed, that's sort of what it's doing for you, okay? So I don't like to mess around and call it m sub y. Just set up your integrals so you have x times your function dx over, and this just stands for the total mass. So that's just the total area times your density, and that gives you your total mass. And then that gives you your x component of the center of mass. But it is m sub y divided by that. Now, I lost where I was there. Okay. This gives you your m sub y, and I think I've done all that here. Okay. Sorry. They sort of are screwy in the book in that they have, no, the slide says the thing that's screwy. This we've covered so far. I have to go back in the slide set to go here, and let me clear this out of the way again. Okay. More generally, if a laminar occupies a region between the graphs of two functions, f1 and f2, over some interval a to b, like this is showing, notice your left and right boundaries of this thing are not functions, it's just x equal a to x equal b. Your only two boundaries that vary are your top and bottom, okay? Well, this is just basically like we had before, except for the fact the length isn't just your of x is the difference. F1 of x, it would be the difference between F1 of x and F2 of x. Now, before we said F1 of x always had to be positive, or F of x always had to be positive. Now that we're taking a difference here, this could be anywhere. All you're interested in is the length from here to here with F1 of x minus F2 of x. So the only requirement here is that F1 always be greater than or equal to F2. You just can't have them crossing. If they cross, this thing gets all screwed up. But as long as F1 is always greater than or even equal to, it just can't be less than F2, then you're fine. Now you don't have to have it being positive. You can take the same shape and put it down here, or over here, or up here, or even straddling the x-axis. It doesn't matter because your length here is F1 minus F2. As long as F1 is always greater than or equal to F2, that's fine. Your delta x is still delta x, so everything works just like it did before. Your moment with respect to the y-axis, and for y, would be this x value here. So your formulas, as long as this is a lamina, the density is equal, then the integral here would be this distance times that. Your numerator would have an x in it because that's how far you are from the x-axis. This x value, x times this difference times dx, divided by, leave off this distance times delta x dx. And that would give you your moment set. And they surprisingly did not give that on this slide set. Okay. Let me see. Ah, here it is. Now, aggravating. Your edition, the old edition, has rho. The new edition has delta. I can't tell you why they changed, but just you see these, that row, that's the same as the delta in the new edition. Okay. Everything else is perfectly fine. Okay. So this is the equation. They don't even number it, do they? In the gray box near the bottom of page 458. Okay. They had a row. We were putting delta in. I'll blow that up a little bit. Of course, I'll blow up my ugly delta too. Okay. Now, that's your moment with respect to the y-axis. In the generic form, okay, let me go back. Okay, this form here, when you just have f of x there, that's when you have your integral like, no, I'm wrong. That one, okay, where you just have one function, f of x. If you're more generic form, like this one, where you have two f of x's, then the form is like this, okay. They have these so squirrely the way they have them organized in the slide set. They're just awful. So this is a moment with respect to the y-axis. In other words, your x distance, your density, and again, in the new edition, this is delta, not rho. Yuck. I can't write. As soon as I go to write, it's going to shrink. Yeah, this is delta. That's delta. Okay. Or rho, whichever you're happy with, that's fine. It's the integral from a to b over your x at the length of the vertical cut, which is the difference between F1 and F2. F1's on top and F2's on the bottom, times your x. That's how far you are from the y-axis. That's why it's y. And then you take this and divide it by the mass, which is just like this, only without the x in there, which is F1 minus F2. The deltas, as long as they're constant, they go out, so you don't even have to mess with those. Now, what if, on the other hand, you have a situation like this, that your upper and lower boundaries are constants, C and D, but now your right and left boundaries are, the right boundary is G1 of X and the left boundary is G2 of X. Okay? I'm sorry. G1 of Y and G2 of Y. Because these are functions of Y, not functions of X. Now your delta is your dy, not dx. That's your thing. You're dividing the interval from C to D along the y-axis, and the dy's, delta y's and dy's, and then the length is the difference of those two functions. Okay? G1 of y minus G2 of y. Sorry. I can't talk. It's a terrible reason that I can't talk. I went to the UAB basketball game Saturday night, so I yelled too much. Sorry. So that's the blown up version of what we were just doing. So what does that yield? Same type thing as we had before, but now is your m sub x. Because if you go back here, where is this line here? Is that the value y above there? So you do all those from C, the line here, to here, to here, to here. Your y's are increasing. Those are y's. Always your length is G1 minus G2. And the dy is always dy. So your function here now, the moment with respect to the x-axis, which is your distance y's, it looks just like the ones with y, except again, I can't write it. If I'm going to write it, it's good. In your book, this is a delta here and a delta there, not a row. Okay? So the moment is from C to D, y, that's the distance from the x-axis, the length of the horizontal cut, in this case it's G1 minus G2, both functions of y, times your dy. Okay. Now, once you get the moments, goodness, my stomach is growling so badly. Okay, once you get the moments, then you do the mass. And the mass is just the density. In our text, in the new version of this is delta, 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 not rho, rho, rho. Okay. And this would be delta, delta, A. And it's the same, whichever you do. You can either do the GY's, G's, or the F's. Doesn't matter. The length times the width. Length times width. The rho is measured by that, or the delta is measured by that. And that gives you your mass. And the mass is the same under the X or under the Y. It doesn't matter. Once you get the mass one way, it's the same on both. So then your center of masses. Now, in the new text, new version, they call this X bar, and they call this Y bar. The old, they call it X center of mass, Y center of mass. So I'll blow this up now. And it's just like we did before. Your X component of the center of mass, X bar, X and CM, either way, is your moment with respect to Y, how far they are from the Y-axis, which is X distance times the area of the strip divided by the total mass, which doesn't have the X in it, otherwise it's identically the same. And the Y component of that center of mass is of X, how far it is from the X-axis, which is a Y value, that's divided by the total mass. Once you calculate the mass one way, you don't have to do it a second. Okay. I think we're ready for example 2. They left out a figure here, I think. Maybe it wasn't in the old book. If you had a center of mass of any kind of a shape here, if you knew where that center of mass was, you could put your finger right under that and lift it, and everything would be perfectly balanced. When I never participated in this, but I heard about it. When I was, say, grammar school to junior high, sometime in that time frame, way back, the actual, sometime a little before that, the guy who won the Olympic weightlifting, heavyweight weightlifting thing, came from the county just south of where we lived. He came from a town called Millen, Georgia, Jenkins County. I believe that's right. And he was a super nice guy too. Big guy, you know, strong as anything. And he would go to speak to classes in local schools. And when they got it set up, they could have the class up on a platform, set up there on sawhorses or something like that. They'd have the whole class up there, and he would walk under that platform. If he knew where the center of mass was, he could lift them and carry them around. He was that strong. He was incredible. But he always made the point, because he was still sort of an inspirational speaker, he said, you've got to know where that center of mass is, otherwise everything falls apart. Okay? That was the key. If you know where the center of mass is, you can do a lot with it. Now, y'all both taking physics, right? You remember your free body diagrams? Basically, you say, let's assume all the mass is at that point. Guess where that point is? Your center of mass. So in real life, you have to do calculations to get it. But then once there, use your free body diagram, do all your calculations. That makes the whole thing a lot simpler. Okay. So anyway, let's go. Here's example 2. Find the moments, so they are making you do the moments, and the center of mass of the lamina of uniform density delta occupying the region underneath the graph of y is equal to, or alpha of x is equal to x squared, okay? And above the x-axis for 0 less than x less than 2, okay? So here's what you got there. Now, okay. Don't fret, because I was beginning to fret. Why do they have this picture in this way? Okay. This is for later, the second part of the problem, for the m sub x's. This is not necessary for m sub y. But what they're saying is set it up to do either one of them. So using our 0 to 2 along x's, then what you're going to do is have, that was unlocked this morning and some student closed it. Sorry about that. All right. This is our setup. So let's just point out, you're going from x 0 to 2. Your y, by the way, says y is equal to x squared, or f of x equal x squared, is going from 0 to 4, because x squared is 4. Okay? So let's shrink this back. And to do your m sub y's, okay, that's the distance from the y-axis. We're going to take our delta x, or dx's. I like to just call it a dx. Okay, they probably call it a delta x. Well, what have you got there? Your m sub y is your density, which is delta, times the integral from 0 to 2 of x, f of x, dx, right? Okay. Distance from the y-axis, the length of this, that's your f of x, times your width is dx. You're integrating that from 0 to 2. Okay? Now, we know the density is delta, so the delta is just going to hang around there, but not do a single thing productive. Well, this f of x here is x squared. So this would be delta integral from 0 to 2, x times x squared would be x cubed dx. What would that be? X to the 4th over 4 from 0 to 2. And this would be your delta. It's what? No. Okay. Oh, okay. 2 to the 4th power is 16 divided by 4 is 4. Okay, the 0 doesn't contribute anything. 4 delta. I'm sorry. I already had written the delta down, sorry. Forgot I had done that. Okay, 4 delta. Now, m sub y, this is where you need the part, I'm sorry, m sub x is 1 with respect to the y-axis, but that's your m sub x. And this is what I don't like about this. It's just sort of counterintuitive, but it is true. Okay. In this case, then you have to make your strip this way. Okay. Well, when you strip this way, you're doing a dy. So this is your thickness here is delta y, or dy. Your length of that strip, the greater length is 2, the lesser length is your function. But if y is equal to x squared, then x is equal to the square root of y, or y to the 1/2, right? Yes? You're kidding me. Just when we're beginning to have fun today. You're right. Yeah, let's just finish this one. It's pretty simple. It's your delta. Now this time the y is going 0 to 4, and your y is the distance from the x-axis, and your function value is the 2 minus square root of y, and then your thickness is dy. Okay. Now, this is 2 integrals. Split it up this way. Integral, the delta on the outside, integral of 2y dy from 0 to 4 minus the integral. Make this as y to the 1/2. Y times y to the 1/2 is y to the 3/2, right? Okay, dy. Okay, and again, this is 0 to 4. So it's your delta times, what would that first one be? Not quite. Integral of 2y dy? Y to the second, evaluated from 0 to 4. That's going to be pretty easy to do. Minus, and what will this one be? A little messier, but still okay. What would that be? Y to the what? Oh, 2/5. 2/5 y to the 5/2, right? Evaluated 0 to 4. That's not going to be too bad. It looks like it'll be sort of bad, but it's not too bad. So this is going to be, I got to go over here somewhere else to do this. This is going to be delta times 16 minus, say again? 32, okay. 2/5 times 32. Very good. Okay? Well, that's going to be messy, but it's going to be delta times, yuck, that would be 80/5 minus 64/5. That's going to be delta times 16/5. 16/5. Okay. And that gives you your y. The one other thing you have to do is the mass. The mass is really pretty easy usually. It's your delta times the integral f of x dx. And you could use either one you want to. F of x is easier, and that's just x squared dx. And what's that integral? Over 3, evaluate from 0 to 2, because you're doing your dx this time. So that would be 8/3, right? Delta. Okay, and this had the delta in it too. So when you go to do your x bar, or your center of mass with respect to the x-axis, that's your m sub y, which was, I know we calculated it. Oh, that was 4 delta over 8/3 delta. Deltas go out, and that would be, say again? 3 over 2, yeah. 12/8, which is 3/2. Okay, and sure enough, 3/2 looks like it's about 1.5. I'm pretty close to being right on it there. And then your y bar is your m sub x, which would be, again, the deltas will go out, 16/5 over 8/3, right? So that'll be 6/5. Is that right? 6/5. And that's what they got. Good for them. Now, why they have, oh no, they didn't. 3/2, okay. So, one other little thing, another way to talk about the center of mass of a lamina, it's also called the centroid. Okay. So the next thing that we're going to do, let me just see what the next slide is. We're going to start at the top of that next page. Top of page 460. We'll start there next time. Actually, we may start with the verbiage from the previous page. Good deal. We'll see.